there were two main things that I wanted you to think about on this daily work. Let's say three. The first one was just the mechanics about how to simplify a product of cycles. Right? So how to take a permutation like this one and figure out what is its second power, figure out what is its inverse. So just that sort of manipulation piece of it. The second was about the concept of order. How to tell, based on this description of a permutation, what the order of that element is as an element of, in this case, it's the symmetric group on 9 symbols, S9, right? And then, still thinking about order, the very last problem asks, what is an example of an element of S9 that has the highest order possible in the group S9? And then also, what is the order of the group itself, and what is the order of the alternating subgroup? And alternating subgroup brings me to my third thing I wanted to talk about in this daily work, which is the idea of the sign of a permutation, even permutations versus odd permutations, and how to tell which is which. So what I'd like to do, I guess, is just to review the responses you got from 1 through 9, paying particular attention to those things. So let's first do the mechanical piece. Is this permutation indeed a product of disjoint cycles, the way that it's been written here?
Yes.
Yes. How can we tell?
They don't have any numbers in common.
None of these cycles have any positions in common. 1, 3, and 7 are only here. 2 and 4 are only here. 6, 8, 5, and 9 are only there. Right. So it's a product of disjoint cycles. How did you find out what its second power was? So what is the secret sauce to how to simplify this product of cycles? What was the key observation you had to make, Grace? One way to do it is to take each position one at a time, move it 2 spaces ahead in its cycle, and figure out where it lands. So 1 ends up in the second power going to 7. 7 ends up going to 3. And 3 ends up going back to 1. And so where we used to have 1, 3, 7, now we have 1, 7, 3. What happens to this 2, 4? What does 2 go to? It goes back to itself. So we could write that as just a cycle with a 2 in it and nothing else. But what is a 1 cycle like this really equal to? Why? Because it's not moving any of the symbols, right? 2 is going to itself, and nothing else is even participating in the cycle. So yeah, any 1 cycle that I can write down is just equal to the identity. All right, what happens to 8, 6, 5, 9 in its second power? 8 goes to, and 5 goes to, and so 8, 5 becomes a 2 cycle. 8 goes to 5, goes back to 8. What happens to 6? And 9 goes back to 6. So there is the second power of this, expressed as a product of disjoint cycles. Keep in mind, too, that the way that we just did it implies that we can consider each of these cycles separately, right? The 1, 3, 7, we can take its second power. The 2, 4, we can take its second power. And this 8, 6, 5, 9, we can take its second power, all individually. So why is this not surprising that we can do 1, 3, 7 squared, 2, 4 squared, 8, 6, 5, 9 squared? In other words, we distributed the power. Why is that okay? What's commutative? Yeah, the fact that these were disjoint cycles means that they commute one with another. And that's exactly when we know that we can distribute the exponent, because we can rearrange these as much as we want to. Because every one of these cycles is, of course, going to commute with itself, because everything commutes with itself, but it also commutes with all the other disjoint cycles that are a part of this permutation. Cool. And then how did you do the inverse? Just so we can get that on the page. For the inverse, I get 1, 7, 3, 2, 4, 8, 9, 5, 6. Do you have the same thing that I have? Do you have something different? You might have something slightly different. Did anyone have something besides 8, 9, 5, 6 for this 4 cycle? Yeah. So you might have something that looks slightly different. Like maybe you have 4, 2 instead of 2, 4. Maybe you have 7, 3, 1 instead of 1, 7, 3. Maybe you have 5, 6, 8, 9 instead of 8, 9, 5, 6. All of those are completely the same thing as one another. After all, remember, it's like these positions are sitting around a round table, right? 1, 7, 3. And when this permutation acts, each thing is just going to move one position to its right around the table. Well, 1, 7, 3 is the same cyclic ordering around this table as 7, 3, 1, which is the same cyclic ordering as 3, 1, 7. All of those look different when we write them down on the page, but they're the same cycle, right? Because they're doing the same thing to the symbols that they're acting upon. So don't be fooled by that. If you're looking for a convention, like how group theorists most like to write cycles, I would say that very often algebraists will defer to writing a cycle with its lowest numbered position first. So I might prefer 5, 6, 8, 9 instead of 8, 9, 5, 6. But again, it doesn't make it incorrect if you write it a different way. Okay, cool. Let's talk quickly about order. What is the order of this permutation?
12.
And why was it 12?
Because the least common multiple of 2, 3, and 4 is 12.
Least common multiple of the... And what are these 2s, 3s, and 4s? Where are those coming from?
The length of each individual cycle.
They're the lengths of the cycles. And that means that they're also the orders of those cycles as permutations in their own right. So the least common multiple of these cycle lengths, these cycle orders, gives us the order of the whole element itself. And again, that's because we've identified this as a product of disjoint cycles. And because they're disjoint, they commute. This is an observation to hang on to for chapter 7, 8, one of those chapters, because it's an instance of a more general phenomenon in abstract algebra, which we might be able to prove now, which is that if A and B commute with one another, then the order of their product is the same as the least common multiple of their orders. Right? So it's the commutativity that makes this the LCM. And so that also gives away the answer to number 7 in a slightly different way. If I want to find an example of an element that has the highest possible order in S9, what kind of an element will it be? How do we get the highest order possible in S9?
Well, it has to be like so I did the 5 and 4. So
Okay.
like it has to be at least common multiple of 5 and 4. So like the two individual cycles, one had the length of 5 and one had a length of 4.
Sure.
Which I found the least common multiple of 5 and 4 was 20, as compared to the least common multiple of 2, 3, and 4, or like 2, 2, and 5, or like 2 and 7.
Yeah.
Which all add up to 9, kind of thing.
Which all add up to 9. Right, exactly. So remember what we said last time, that the order of an element is completely determined by its cycle type. What lengths of cycles, disjoint cycles composed together, give me that element. And so in S9, we have this huge list of, in fact, there's 30 different cycle types that we can make inside of S9, because there's 30 different integer partitions of the number 9. So we take and we figure out, how do we split up 9 into a sum of integers, positive integers. One way to do it is just to write 9 and just take a 9 cycle. Another way to do it would be to do 8 plus 1. So an 8 cycle composed with a 1 cycle. But a 1 cycle is just the identity, so this would just be an 8 cycle. Or we could do a 7 cycle composed with a 2 cycle, or a 7 cycle composed with a pair of 1 cycles, which are the identities, and so on and so on. So there's 30 different partitions, integer partitions of the number 9. And the one that has the highest least common multiple, as Caitlin is saying, is the one that has the cycle type 5 plus 4. Okay? I don't really know if there is a more intelligent way to do this other than list out all the different cycle types and figure out which one has the highest LCM. Maybe there is a smart algorithm or a formula or something else that we can find to do this, but I'm not aware of it. Maybe you can find one. Maybe that's a good undergraduate research project. But anyway, 20 is the best we can do inside of S9, which is a little bit surprising because how many elements are there in S9? Yeah. 362,880. How'd you get that?
N factorial.
9 factorial, exactly. So there's 362,880 elements. So that's the order of the group, S9. But none of those elements has an order higher than 20. Why is this at least a little bit surprising? Or why is it different than what we saw with cyclic groups in our last chapter? If this were a cyclic group, what what would be the highest order of any element in this group? If this were a cyclic group, then there would have to be a generator for it, and that generator would have to have its order equal to the order of the group. Right? So if S9 were cyclic, we would have to be able to have an element of order 362,880. And not just that, because that element of order 362,880 exists, so too would elements of any order that divided 362,880. Right? In particular, 181,440, which happens to be the order of A9, right, the alternating group. But there's no element of that order either. There's also no element of order 40, which is a divisor of 362,880. The highest order we can get in S9 turns out to only be 20. So it's a little bit surprising somehow, I think, that we can have a bunch of permutations, elements in a group, and none of their element orders are any higher than 20. But taken together, there's 362,880 of them. Right? So that is one thing that makes symmetric groups very different from cyclic groups in the general case, is that the orders of elements tend to cap out pretty quickly, determined by the largest LCM of the various cycle types that we can have in that group. I just happen to pick one example of a 5+4 cycle, and all I had to do is just make sure that my cycles were disjoint, so that their order was the least common multiple of their cycle orders. So let's tackle question 5. So which of the permutations in this list are elements of the alternating group? So first of all, how do I know when a permutation belongs to the alternating group? What has to be true about it? Yeah. The sign of the permutation has got to be even. So if I look at my original sigma, is this an even permutation or not? How can I tell?
Yes.
It is. Why?
Because there's an even number of transpositions that can be made from it.
Yes, there's an even number of transpositions in sigma. And so to figure that out, we have to know, well, 2,4 is definitely already a transposition. But how do I envision 137 as a product of transpositions? How many transpositions comprise 137? 2 of them. It's a 3 cycle, and therefore we can write it as a product of 3 minus 1 transpositions. Right? 8659, what happens with it? 89, 85, 86. It becomes a product of 3 transpositions. 4 cycle, 3 transpositions. 3 cycle, 2 transpositions. 2 cycle, 1 transposition. Right? And so all in all, we add these up, we find out that there's 6 transpositions that can be used to write down a permutation which does the same thing as sigma. And so yes, sigma itself is a member of the alternating group. What does that tell me about sigma squared? How many transpositions do we know for sure we can write sigma squared with if sigma can be written with 6? Well, imagine writing this permutation twice. Right? Sigma squared. This composed with itself. How many transpositions would I write? 12. And 12 is what kind of number? Sure. So because sigma was even, sigma squared is going to be even. But what if sigma is odd? What if sigma is an odd permutation? What can we say about sigma squared? Really? How do we know it's going to necessarily be even? If sigma is odd, why must sigma squared be even?
Because an odd plus an odd is an even.
Right. So this is somehow always true for all sigma. Right? No matter what permutation you give me, whether it's even or odd, if I square it, I'm going to get a permutation that's got to be even. Right? Which was one of the reasons we talked about in our last class why the set of odd permutations doesn't form a subgroup. Right? Because it doesn't have closure. Because odd composed with odd no longer gives me odd. Right? Odd composed with odd is going to give me even. All right, well, sigma is even. What do we know about sigma inverse? It's also even. Let's dwell on that for just a second. Suppose I wanted to know how to find the inverse of this product of transpositions. How could I find the inverse of this list of transpositions? What is a theorem or a principle that I can use to find the inverse of this big, long product? The shoes and socks. Except instead of having just one pair of socks and one pair of shoes, I'm somehow wearing maybe like 3 pairs of socks inside one another, and then 3 shoes on top of one another. Same principle, right? Shoes and socks can tell me that this inverse is just the product of the inverses in the opposite order. So I would have 8, 6 inverse, followed by 8, 5 inverse, followed by 8, 9 inverse, followed by 2, 4 inverse, 1, 3 inverse, 1, 7 inverse. But what are each one of those inverses? Itself. Why? How do I know that each of those transpositions is its own inverse? One space to the left is the same thing in one of these 2 cycles as one space to the right. Or another way to say that is trading places between 2 elements is the very same operation as trading those places back. Right? So each one of those elements is its own inverse. But importantly, how many transpositions does it take to write down this inverse? The same number that it took to write down the original. Right? So if sigma is even, sigma inverse is even. If sigma is odd, sigma inverse will be odd as well. So actually, the set of odd permutations does have the inverse property, right? Even if it doesn't have the identity property, right? Which is a little bit odd. And then finally, sigma cubed also is even, because we can write it with 18 permutations. So what I want us to do with the rest of our time today is to really go a little bit deeper on those alternating groups. So let me show you the 4 questions I want us to tackle. Your groups are going to each get 1. So here are the questions. And whatever of your question we don't finish during the hour, I'm going to invite you to talk about in your Slack channel between now and Friday. I'm also going to try and schedule a live stream problem-solving session tomorrow morning. I'll send out some information about that as well, and I can address some of these questions there if you like. So the first question is, I want to have one group rethink the maximum order question, but instead of maximum order in S9, think about how to find the maximum order of an element in A9 instead. So let's give that to, I'm going to give that to the diamonds group, so you all tackle that one. And how about hearts get the second question? Can you write down a proof for why A3 is an abelian group, but A4 is not an abelian group? And then our remaining groups, so the spades and the clubs. These are 2 similar questions, and since the spades group is a little short, what I'd like you to do is just merge your 2 groups and think about both of these questions. So here I have a subset of elements of A4. It's the subset consisting of all elements whose square is the identity permutation. So everything which has order 1 or 2, I suppose, is how we can see this. Is that set a subset of A4? And then separate question, would it be a subset of A5 in those cases?